All right, in this video we're going to review for the AP Stats test, and we're going to talk about the binomial model. Now the binomial model involves mean and standard deviation, involves probability, and kind of involves a little bit of the normal model as well. So there's a lot of topics involved in a binomial problem. So first, let's make sure that we understand the binomial can be used as a random variable and with probability. Again, watch why I thought it deserved its own video. So a situation in which you can use the binomial model is very, very specific. First, there can only be two outcomes, success and fail, in each trial. So at the end of a trial, at the end of that random event, only two things can happen, good or bad, success or fail. The outcome of one trial must be independent of the next. This is huge that allows us to kind of use multiplication, because remember the multiplication rule can only be used if the two probabilities, or if the two events, excuse me, are independent of each other. All right. Third, the probability of success must stay the same for every trial. So if the probability of success is, say, 20%, that when you repeat and repeat and repeat and repeat, the probability must stay 20%. So please be very careful that that has to be true. The probability cannot slowly be increasing or decreasing. That's not binomial. Fourth is you must be given a set number of trials. That's what makes it binomial, is that you not only know the probability of success, P, but you also know how many trials you're looking at. And that's why it's called the binomial model. Bi meaning two. You know the probability of success, P, and you're given the number of trials. So an example would be true and false tests where you just guess. So again, every outcome is true or false, success or fail. Now, I want to be very clear here. A multiple choice test could also be binomial. If you look at A, B, C, D, right, 4 choices on a multiple choice test, if you consider this correct and all the others together failure, then that would technically also be binomial. Even though there's 4 choices, you know, group them as right choice, wrong choice. 3 of them are all wrong, so you'd group them together. That could still be binomial. Another example that's very common you see is dealing with batteries, right? So you either have a good battery that works or you have a defective battery. So it's either successful and then it works, or it's failure and then it doesn't work. But also be careful. We use the term success and fail, but we don't always mean a good thing and a bad thing. Success is just the term we use for looking for something that you want to find. So if you're looking for, you know, a person to have cancer and you're involved in a problem that deals with cancer, well, then you're looking for cancer. So that would be a success. But again, I don't think anybody would actually consider having cancer a success. But again, when we say the word success, we mean finding what we wanted to find. Whether that thing we're trying to find is good or bad, who cares? Okay, so let's talk about a binomial model as a random variable. So 15% of batteries are bad and don't work. So 15% of batteries are defective. So that is our P, right? The probability that we find a defective battery is 15%. And 1 minus P would be the probability that we find a good battery, 0.85. So this is what I was talking about. Finding a bad battery would be considered success. Finding a good battery would be considered failure. Even though that logically doesn't make sense, we're looking for bad batteries. So that would be success. So if I randomly inspect 5 batteries, how many could be bad? So that's the random variable. A random variable is, what could happen? I don't know. Well, we use a capital letter for the random variable. There could be 0 bad batteries. There could be 1 bad battery. There could be 2 bad batteries, 3 bad batteries, 4, or oh my goodness, all 5 could be bad. And that's what makes the random variable. Now 5 is how many batteries I'm looking at. That is my N. And as I said, you must be given 2 things. The probability of success, failure should come free with that. And then you must be given a set number of trials. So I was given 5 batteries. But be careful, that actually means 6 things can happen because you've got to include 0 there as well. So 0 could be bad, 1, 2, 3, 4, 5. Now a true random variable also has probabilities connected to it, and that's where we need the binomial model. All right, so let's find the probability of an outcome in the binomial model, okay? So what I'm going to do is I'm actually going to build this model again, and then we're going to find the probabilities of it. All right, so I can either have 0, 1, 2, 3, 4, or all 5 batteries be defective. All right, now I actually want to start with 1, and you'll see why as I kind of go through this. Now, I want one bad battery. So that means if I think about my 5 batteries, 1, 2, 3, 4, 5, those are my poor drawings of batteries, one of them has to be bad, which means I need one of them to have that 15% chance of occurring to be the bad. The other 4 are good, that would be 0.85. So I need 0.15 to the first for one bad battery, and 0.85 to the fourth for 4 good batteries. Okay, so let's just say that this one right here is the bad one. That's the 15% chance of a bad one. All the other ones are 0.85. Now I'm multiplying, but remember, order of multiplication doesn't really matter. So I'm going to just, as long as you got 4 0.85s and 1.15, you're good to go. So that's where my notation is there. But there's something extra I have to add on to this. How many different ways can one of them be bad? And that's the trick to the binomial model. I mean, I hope understanding this part is easy. One bad battery, 4 good batteries. But which one's my bad battery? This one could be the bad battery. Or this one, or this one, or this one, or this one. There's actually 5 options for which one could be the bad battery. And that's what goes out in front. There's 5 different ways that this can happen. All of them have one bad battery, 0.15 to the first, and 4 good batteries. But there are 5 distinct different ways that that can happen. So now that's pretty easy to understand, but let's move on to 2 real quick. Okay, 2 bad batteries. That would be 0.15 to the second, 2 bad batteries. And that would obviously mean that 3 of them are good batteries. So 0.15 to the second, 0.85 to the third. How many different ways can this happen? Well, I'm going to grab a different color here. These could be my 2 bad ones. 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 The first and the last could be my... So the point I'm trying to make is things get a little bit confusing here. So we have a way to make this easier. Now our notation is like this. We're going to say 5 batteries, we're looking for 2 successes. Now this right here is a notation, these giant parentheses. So 5 batteries, choose 2 to be successful. Now, you can actually calculate this on your calculator. And so instead of you having to figure out how many different options there are, just let your calculator do it. Now there is a formula for this. Technically the formula is 5 factorial over 5 minus 2, which is 3 factorial, times 2 factorial. And you might be like, what? Okay, you don't have to worry about that formula because there is a shortcut on your calculator. All you got to do is type the 5 in first. Then you're going to go to Math, slide over to Probability, PRB, and go down to NCR, option 3. And what you're telling the calculator to do is say, okay, I got 5 trials. I want to choose 2 of them to be successful. Now they use R to represent how many successes, whatever. Call it R, X, K, W, who cares? The point is, what this is going to do is this is going to calculate how many different ways. If you got 5 batteries, how many ways 2 of them could be defective. And they tell us there's 10 ways. Let me go back to the previous problem, what we just did. We did 5, and we wanted to say, let's choose one of them to be defective. And there's 5 ways for it. Now that's a little bit easier to understand because it just could be any one of the 5. Could be the one defective battery, hence 5. Well, you know, that's pretty easy. But again, 5 choose 2. I mean, I don't know if I want to list all those different options and think about them. So that's why we use the calculator. So that tells us that there are 10 different options for 2 bad batteries. Okay, let's move on to 3 bad batteries. So that's 3 bad batteries. And if 3 are bad, then only 2 are good. Well, again, let's figure out how many ways that can happen. So we do 5, choose 3. So this is 5 batteries. Select 3 of them to be successful, and that would be 10 as well. Okay? And again, you could go through and try to find them all. You know what I mean? No first 2. Yeah, but again, that's just a waste of time. And again, the formula is 5, 3. It's written like this with the parentheses. And again, if you really want to know the mathematical way of calculating that, it's 5 factorial on the bottom, and then 3 on the top, 3 factorial on the bottom, and then you do 5 minus 3 to get 2 factorial, and that goes on the bottom as well. But again, don't stress out having to remember that formula. Just make sure you understand how to use your calculator. So there's 10 ways for that. All right, let's talk about 4. All right, so there's 4 bad batteries. That would only lead 1 good battery. And then again, go to my calculator. How many different ways can this happen? If I hit second enter, it actually pulls up what I just typed in, and I can just change that to a 4. So 5, choose 4. 5 ways that can happen. Okay? Let's go back to the top real quick and do 0. 0.15 to the 0. No bad batteries. All 5 are good. Now, do I really need 0.15 to the 0? No, because anything raised to 0 is 1. But it is important to understand that there are 0 bad, all 5 good. I like to write it that way so I can see it. Now, how many different ways can this happen? Well, this is probably the most common sense way. There's only one. There's only one way all 5 could be good. All 5 are good. Good, 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 good. All 5 good. There's only one way that can happen. But if you want to use your calculator, you can. If you want to confirm that there are, how many different ways can I have 5 batteries and choose 0 to be bad? Well, there's only one way, and that one way is that they're all good. And I could come down here for this one as well. All 5 are bad. That would be 0.15 to the 5th. All 5 bad, and that means that 0 are good. Now, anything to the 0 is 1, so this doesn't really matter that I have it there, but I do like to see the pattern, 5 bad batteries, 0 good. And again, there's only one way that can happen as well. All 5 are bad. That's it. It's only one way that can happen. But again, if you do need some confirmation on your calculator, 5 choose 5 does get you 1. All right, now what I have to do is actually go and calculate these probabilities. So that for that first one, 1 times 0.15 raised to the 0. Now again, I don't have to type that in because I know what that is. And then 0.85 raised to the 5th. So, one way this can happen, 0 bad batteries, all 5 good batteries, 0.4437. And now I just got to go and calculate each one of these probabilities. And boom, there's all of them through the power of, pausing my video and figuring them out. There they all are, so rather than waste time going through it all. But again, you just got to use your calculator and calculate all of those. And again, what you'll notice is that the most likely outcome is none of them are bad. And this is definitely a skewed to the right distribution, because towards the right, it's a lot less likely. And again, there's only a 15% chance of a bad battery, so it should make sense that if all 5 of them are bad, that would be pretty rare. That would be pretty significant for all 5 to be bad. Something weird's going on there because the probability of all 5 being bad is pretty low. Now, I do want to teach you a quick shortcut on your calculator to calculate these as well. If you go under second vars and you scroll all the way down to Binomial PDF, what you could do is you can have, instead of typing all this in, your calculator could do it a lot faster. Your calculator could actually do all the work. So what you do is you type in the number of trials. So I got 5 batteries, number of trials, number of batteries. The probability of success, this is the probability of what you're looking for. Since I'm looking for bad batteries, I'm going to type in 0.15. And then you simply tell it how many you want. So I want 1 bad battery. It'll calculate the probability for you, 0.3915. So it does all the work for you. And all you got to do is go back and change that 1 to a 2 for 2 bad batteries. And I get 0.1382. So it does make it very fast and very convenient to do that. So that's how you do the binomial model. If you're kind of looking for like a formula, a generic formula for this, what they say is, okay, n choose r, and then you have p raised to the r, that's how many successes you want, and then you have 1 minus p raised to 1, or n minus r. So the idea here is n is how many batteries you have, r is how many successes you're looking for. So you need that many successes, and then whatever the difference is, how many failures you are. So again, if I'm looking for 2 bad batteries, 5 minus 2 would be 3 good batteries. So that's kind of the generic formula there. And that formula is actually given to you on the AP formula sheet as well. All right, next question we could ask ourselves is, what is the expected number of defective batteries out of 5? Now, if you remember from our video over random variables, this is discrete, right? I have 6 possible outcomes for how many defective batteries there could be, and I have the probabilities. You could enter this into your calculator into list 1 and put the probabilities in list 2, and then you could run a one variable stats list 1 with frequencies set as list 2, and it'll tell you the mean. But when you're working only with the binomial model, there's actually a very easy formula. To find the expected number of defective batteries, or to find that the expected number of successes in any binomial, the formula is very simple. It's simply n times p. What an easy formula. So for us, that's going to be 5 batteries times 0.15. It actually just makes sense, right? If you got 5 batteries and 15% are supposed to be bad, you just multiply 5 times 0.15, and you get your answer. I mean, it's really easy. It's 0.75. Now, a lot of people, that'd be 0.75 batteries. Now, a lot of people will say, well, you can't have 0.75 batteries. Yeah, but this is an average in the long run. Like if I were to grab 5 batteries and count how many were bad, you know what's going to happen most often? 0. If I do it again, maybe 0. Do it again. Okay, 1. Do it again, 0. Do it again, 1. Do it again, 0. Do it again, 0. If I keep grabbing 5 batteries and looking at how many are defective, I'm probably going to see a lot of zeros and a couple ones. Very rarely will I see a 2 because the most likely outcome is 0 and 1. And again, every now and then you might see 2. You might even see a 3. 4 and 5 are pretty rare. My point I'm trying to make is the average after many trials of 5 batteries would be 0.75. In the long run, I would only expect 0.75 batteries to be bad. But of course, it could deviate. So there's a standard deviation here as well, and it's a pretty easy formula as well. It's the square root of n times p times 1 minus p. Pretty easy formula here. So that for us would be the square root of 5 times 0.15 times 0.85. Now keep in mind that these formulas only work with the binomial model, so don't just blindly use these formulas if you don't know for sure that it does follow a binomial model. And I believe that would round to 0.80 batteries for the standard deviation. Okay? All right, so here's the next question. If a sample of 5 batteries is inspected every day for 4 straight days, okay? So we're going to look at 5 batteries on Monday, Tuesday, Wednesday, Thursday. 4 straight days, we're going to look at 5 batteries each day. So 4 total samples. What is the probability that there are no defective batteries found in any of the samples? Well, I have to use a little bit of old school probability to understand this. So the probability of no defective batteries is 0.4437. Now that's for one sample. In one sample of 5 batteries, the probability that none of them are defective is 0.4437. Well, I'm trying to find the probability that this happens 4 straight days. So on the first day, I need no defective batteries, 0.4437. And then I need it to happen on the second day, so I need another 0.4437. And then I need it to happen on the third day, so I need another 0.4437. And then I need it to happen on the fourth day, another 0.4437. So essentially, because these are independent events, I'm allowed to just multiply them as long as the probability stays the same, and that's the whole point of it being independent. So 0.4437 to the fourth would be the probability of me finding 0 defective batteries for 4 straight days. So 0.4437 raised to the fourth. So 0.0388. So kind of a cool problem, pretty easy problem, but it kind of incorporates, the binomial model. So that's how I got the 0.4437, but also incorporates the ideas that we learned back in probability. Okay. Let's take a look at another problem. So a game is played where you must simply guess which of 4 boxes a prize is under. After each play of the game, the prize is randomly placed under one of the 4 boxes again. That keeps the probability of you guessing correctly the same, right? So with 4 boxes, the probability of you guessing correctly is 25%. So the probability I guess correctly is 25%, and the probability I get it wrong, failure, would be 0.75. All right, I'm going to play the game 5 times. What is the probability you win exactly 3 times? Okay, so that would be 5 games. I want to win 3 times. Now, again, this first part right here represents that I don't care which 3 I win. I could win the first 3, I could win the last 3, I could win the first and then the middle 2. Who knows? So this is what I'm going to use my calculator for to figure out how many different ways you could choose 3 wins out of 5. But I do know that I need 3 wins. That would be 0.25 to the third because the probability of winning is 25%. And then I would also need 2 losses, 5 games, 3 wins, 2 losses. So again, the first thing I'm going to do is 5, and I'm going to go and grab my NCR to figure out how many different options there are. So how many different ways can you win 3 out of 5 games? 10 ways. Then I'm going to take that 10, multiply it by 0.25 to the second power, multiply that by 0.75 to this, I take that back, sorry. The 0.25 should have been to the third power for 3 wins, and then 0.75 raised to the second for 2 losses. So there's my probability, 0.0879. 0.0879. So I got an 8.79% chance that I win exactly 3. All right, what is the probability you win at least once? This is a tricky question. A lot of kids mess up. At least once means 1 or more. So that means you win 1 or 2 or 3 or 4 or all 5. Now that's a lot of work because I'd have to go and do what I just did for 1, 2, 3, 4, and 5. So you know it's a lot easier to solve this problem? Let's just find the probability you win none. let's find the probability that you win none and then do 1 minus that. Because, at least 1 means 1 or more. So if I get rid of none, the opposite of getting rid of none, the opposite of none is 1 or more. So keep that in mind. That can be a big help on the test. So the probability of no wins would be 5, choose no wins, 0.25 to the 0, no wins, 0.75 to the 5, all losses. You never win. Then I got to do 1 minus this. Now calculating this is actually really easy because how many different ways can you have no wins? 1. What is 0.25 to the 0? 1. So all I really need is 1 minus 5 straight losses. The opposite of losing every single time would be you win at least once, right? So it's actually pretty easy math to figure out. So 1 minus 0.75 raised to the 5th, and that's what gives me 0.7627. So if I play this game 5 times, the probability I win at least once is about 76%. All right, another question, final question. This one's a cool question because it actually incorporates normal model as well. A robot is designed to throw a baseball, and the distance the ball travels follows a normal model with a mean of 168 feet and a standard deviation of 12.3 feet. If it follows a normal model, that makes probability really easy. What is the probability a baseball is thrown under 145 feet? So it said a baseball. So it's talking about one baseball. So if I think about this normal model, I'm supposed to throw 168 feet, but it does deviate. So all I got to do is find the z-score, because if it follows a normal model, I could use Normalcdf. So I'm going to find the z-score for 145 by subtracting the mean and dividing by the standard deviation. And let's see here, 145 minus 168 is negative 23 divided by 12.3. That is a z-score of negative 1.87. All right, now all I got to do to find the probability that a baseball is thrown underneath that is I'm going to grab Normalcdf. I'm going to start way down at negative 999 because I want to look below. I want to look under this z-score, so I'm going to start really low. I'm going to stop at my z-score of negative 1.87. And I get 0.0307. So the probability that a baseball, I'll use just a ball for baseball, is thrown under 145 feet is 0.0307. Okay? So I found the probability. Again, that's because if you actually build the normal model and put 168 in the middle, 145 would be pretty low, so being underneath that would be pretty unlikely. All right, if the robot throws 10 balls, see now I'm not throwing 1, I'm throwing 10, that now makes this binomial, as long as the probability stays the same, and that's important. So what is the probability that exactly 3 of them will travel less than 145 feet? So now this becomes binomial, because I got 10 balls, and I'm looking for 3 of them. So 10 baseballs, I'm trying to find 3 of them to be under 45, or 145. But again, I don't care which 3, it could just be any of the 3, which is why I got to do the binomial model. And the probability that a baseball is under 145 is 0.0307. I need 3 of those, because I need 3 baseballs to be under that. And then, the probability of being over 145, or the opposite, would be 1 minus 0.0307. That would be 0.9693. And I need 7 baseballs to do that. So again, I need 3 baseballs to be under 145, which I already found the probability for. I need 7 baseballs to do the opposite of that, which is 0.9693. But again, I need that 10 choose 3 to tell me how many different ways it can happen. Because I don't care which 3 baseballs do this, I just need 3 of them. So 10 choose 3 tells me how many different options there are. Then I'm going to take that 120 and times it by 0.0307. Raised to the 3rd, multiply that by 0.9693, raised to the 7th, and the probability is extremely unlikely. Oh my goodness, look at all that. Actually, I messed this up. I got to re-enter this. I knew something was fishy there. There should be a multiplication sign right after this 3. I'm so sorry. Okay, so there's the probability, 0.0028. 0.0028 is the probability that this occurs. So again, kind of a cool problem because I used the normal model, but then I had to use the binomial model because now I'm talking about 10 baseballs. So kind of a cool problem. Hopefully it all makes sense. And the binomial model, there's usually a couple questions on the AP test about it, so make sure you do a quick review for it.